Hi, everyone. So we'll pick up today where we left off last time. So last time we were talking about NMR, and we were making our ways towards an NMR quantum computer. We started talking about the architecture, how we apply, what are the qubits, how we apply the gates, and we left off. So I described some molecules, and then we left off with the couplings. Okay, so we talked about the fact that in an NMR quantum computer, we have this ensemble of molecules, and each molecule plays the role of a quantum computer, and what we're measuring is the average magnetization signal from this ensemble of molecules. And we started talking about the interactions. So I'll continue from that point. Before I continue, are there any questions with respect to last week? Things that need clarification? What we're going to do today is I'm going to finish off the interaction, and then I'm going to show you how we do the single qubit and 2 qubit pulses on this ensemble. And that basically enables us to do computation, or the gates, sorry. And then we will talk about how we do the initialization and the readout. Okay, so that's kind of like the flow for the NMR quantum computer, and then we're going to move to talking about light. Okay, so are there any questions with respect to what we saw last week?
Just to be clear, each molecule is a computer?
Yeah. So you remember I gave a couple of example molecules. Maybe.
And for 2 qubits, we need molecule with 2 free spin, 3 electron.
You need right. Each qubit is a nuclear spin. So I'll write here the example for example, for a 2 qubit algorithm, you can use a chloroform molecule, which is 3 chlorine atoms which are not used, and they're connected to a carbon and hydrogen. And the carbon and the hydrogen, these are the 2 qubits. The nuclear spins of the carbon and the hydrogen play the qubits in this molecule. One has, remember, at around the field of 11.7 Tesla, one has the splitting of about 500 megahertz, and the other has a splitting of about 126 megahertz. Okay, so those are 2 qubits which are going to be very distinct frequencies. Okay, and the interaction between them, this is what we haven't talked about. This is what we're going to talk about now, and we're going to see how the interaction causes a slight splitting of the energy levels, and that will allow us to create conditional pulses. So we'll see how we do a conditional phase gate using this interaction. Okay.
I also have a question.
Yes.
Is there some way to make some artificial molecules or something to scale this method, or is there a possible scale up for this thing?
Well, we're going to talk about NMR strictly is really non-scalable. It gets stuck because each molecule, the molecule is your quantum computer. So you want a quantum computer with 50 qubits, you need to scale it up. Okay, and also the fact that you're measuring averages is highly limiting. So we're going to see, we'll finish all the steps and then we'll be able to discuss it maybe a bit more intelligently. But the final answer is this NMR technique is really non-scalable, and you got to find something else. And this is why we're going to move on to talk about other technologies that are more controllable and more appropriate. Because here you're just taking the solution and it has all these molecules, and whatever molecule you can find, that's it. So maybe you can get a few tens of qubits in this thing, but not much more than that. Okay. At the end, if I forget, I should not forget because I've written it down, but we'll have a small discussion about the scalability of this platform. Okay. All right. Any other questions before I continue?
Hi.
Yes.
Just to see that I got it figured out. You also need each molecule in your NMR setup to be different, so you can distinguish them with frequencies.
No, each molecule is identical. So think about what's happening in the NMR setup. Remember, you have this liquid, and it has many of these molecules. Each of these dots here represents a molecule. Okay, and if you remember the setup that we had last time, you had a coil around here that was sending RF pulses, right? And we had a big, large B field. Okay, and when we're talking about the interaction, we're basically talking about our interaction with one molecule. But you can think of, basically you have this, this spread of many molecules. If everything is identical, if this B field is perfectly uniform, then everything is perfectly uniform, okay, then you can think about you have one molecule, but you're just remeasuring many times, okay?
But in that molecule, what I meant to ask was, you need to have different kinds of atoms, because each one has a different frequency. You can't have two carbon atoms in the same molecule.
Well, you can have two carbon atoms, but they need to have a strong enough interaction to cause a splitting. So last week I showed another molecule. This one is a 3-cube, one that was used to do teleportation demonstration. And I don't know the name of this molecule, but it looks like this. So you have two carbon atoms and they're strongly interacting. So the strong interaction causes a splitting of their energy levels. And there's a hydrogen atom and 3 chlorine atoms like this. Okay, and these three things.
So effectively, they see different frequencies.
Yes.
Those two carbon atoms.
Exactly.
Yeah, okay.
Effectively, they see different frequencies. And what we're going to see now is that even this interaction, which is weaker, or this interaction here is weaker, causes a slight splitting, and this is what's going to enable us to do conditional rotation. So we're going to see that right now. Okay. Any more questions? Okay. So let's continue where we left off last time. So we started off with the spin-spin coupling, and we saw that that's well, did we do that last time? I don't remember. Can someone remind me where did we do the spin-spin coupling, or did we stop at the spin-electron coupling? Anyone who remembers?
I think it was the spin-electron.
We did this, right?
I think.
Did we do the... hang on, I'll write it down. So I wrote down first the interaction, this interaction, and then we justified why it is very tiny and can be neglected. But I don't remember if we did that or not.
Last time...
did we discuss this?
We did discuss, we started to discuss a spin electron.
Okay, good. So we discussed this, and then we started, okay. So we moved on to the spin electron. Okay, and it's really, think of it as spin electron spin interaction. Remember, because it's you have your nuclear spin, another nuclear spin, and the nuclear spin is interacting with the electron, and that electron is interacting with the spin. Okay? And this type of interaction is usually referred to as J coupling, just because of the letter J in the Hamiltonian that is used for this. And this interaction Hamiltonian, mark it J up here, in its most general form gives us H bar J over 4 sigma 1 dot sigma 2. So this is the effective interaction. It's just two spins and they're interacting directly with some strength J. And this J is just some number that's given by this whole process that we talked about. Okay, but at the end it's just a number. Now, if we break this apart into two components, the Z component and the X component, so we'll have H bar J over 4 sigma Z1 sigma z2. So these are the z component of this thing. And then we have h bar j over 8 sigma 2 plus sigma 1 minus plus sigma 2 minus sigma 1 plus. Okay. And this is a transverse exchange interaction. Okay. Reminding you just that sigma plus is sigma x plus I sigma y, and sigma minus is sigma x minus I sigma y, so you can plug them in and see that all this thing will just give you this. And the reason that I broke this up into these two parts is that now it's easy to see that, suppose that our two spins, our two nuclear spins, are far away detuned in frequency. Far away detuned such that their detuning, delta, this is the detuning of the two frequencies, is much larger than J. Now in this case, and what I'm going to do now is I'm going to give you these hand-wavy arguments, but when we have further discussions and we talk about, in the next chapter, a bit more of light-matter interaction, we'll look at, and when we talk about the Jaynes-Cummings Hamiltonian and so on, and more with respect to other technologies, we'll do this math a bit more rigorously, okay? But now I'm just giving the hand-wavy argument that you can see that what this term does is it destroys the excitation on spin 1 and creates on spin 2. Okay? So in a hand-wavy argument, you can see that if they have different energies, this doesn't conserve energy. So when they're far detuned away from each other, this term is going to be suppressed. Okay? So this term is going to be suppressed. Okay. Now, if you want to go ahead and do this yourself, you can just, what you can do is, in this small parameter, you can derive this in perturbation theory. And like I said, we'll do it later in the course, but just but just so you feel more comfortable with what's going on and what's behind what I'm neglecting here, if you do perturbation theory in this small parameter, then a term like this, J sigma plus sigma minus plus sigma minus sigma plus, this term over here, under perturbation theory, we'll just go to something like J squared over delta. Delta is the detuning between the two spins. Sigma z. Sigma z. So, let me put just 1s and 2s here. 2, 1, and 2, 1. Okay? So even if you take the perturbation theory and take the first term, you will still get the sigma z, so you can add that to this thing. Okay, so this thing is basically going to contribute the same thing when the two qubits are far detuned from each other. Okay, so all that's happening here is basically that the interaction, so our overall interaction, and this is the main point that I wanted to show you, the overall J interaction is going to be some h bar j over 4. I don't call it j tilde because it's some different effective j, but there is some effective j. Okay, sigma z1, sigma z2. And if you add it to the regular nuclear spin Hamiltonian, remember omega q sigma z, then you have your frequency for one qubit, frequency for another qubit, and then another interaction term which shifts the energy by a small parameter j dependent upon the state of the other qubit. Okay? So let me write this explicitly. on the next board. Okay. So our Hamiltonian, okay, let's give this a title. So what I'm going to write this is now explicitly for a 2-qubit example. Okay? So we're going to write this explicitly, the Hamiltonian. So our Hamiltonian, h over h bar, is just going to be omega q over 2, omega q1 over 2, sigma z1. This is qubit number 1. Omega q2 over 2, sigma z2, qubit number 2. And our interaction term, some j, sigma z1, sigma z2. Maybe hang on, I want to change color. Just a second. Maybe I'll write the interaction term in red. Let me get it. J, sigma z1, sigma z2. Okay. And now if I write the energy level system, so I'm going to draw now a diagram for the energy level system, for the energy levels. So this will be the state 0, 0. Okay, 0 can be up and 1 can be down, or we can do arrows, it doesn't matter. And then we will have the state, maybe we'll put down here, some state, that 0, 1, yes?
It's the Hamiltonian divided by what?
H bar. It's just because I omitted H bar from everywhere. Here it's 1, 0, and here we have the state 1, 1. So the black lines, they symbolize the uncoupled Hamiltonian. So this will be uncoupled. These are the uncoupled levels. So if we only took this part, these would be, let's say, our energy levels. Okay? And if we write the spectrum, so if we have the spectrum of these uncoupled spins, basically what you will see is you will have some frequency here. Okay, suppose that this is the spectral response of some experiment. And then you would have here omega q1, for example, and omega q2. So this is the uncoupled system. Now we add this coupling term. And what this coupling term does, so it causes a splitting. Okay? So now omega q is going to split into two peaks. And the difference between them is going to be 2j. And omega q2 is also going to split into 2 peaks with 2j. These 2 peaks are basically what is happening here. So if you look at the Hamiltonian, you have, when the 2 qubits are in the ground state, you have some ground state energy. Now qubit 1 is in the excited state. This is, for example, this energy. But there is another little term, okay, that depends whether qubit 1 is in this energy, is in the excited state, or is in the ground state. Okay? So if, for example, I draw, so what's happening is that we're going to get these splittings. So now the energy levels are going to shift a little bit. So for example, so each of these peaks is going to correspond to a different transition. Okay, if before, this peak over here, omega q1, corresponded to this transition from this to this. Sorry, did I mix? let's call the left one 1 and the right one 2. So this transition. Okay, sorry. So this peak over here corresponded to the transition of this from 0, 0 to 0, 1, but also from 0, 1 to 1, 1. Okay? It simply takes qubit 1 from 0 to 1, from 0 to 1. Okay? And also this peak over here, it corresponded to this transition. They're supposed to be the same, just my drawing is very bad. Okay, it's not to scale, but they're supposed to be the same. But now that we've added this interaction, you can see that this, or basically these two, are no longer the same. Okay, so for qubit 2, it is split into two frequencies. So now we have this transition, which takes qubit 2 from 0 to 1, conditioned on the fact that takes qubit 2 from 0 to 1, conditioned on the fact that qubit 1 is in 0. It is now at a different frequency than this transition, which takes qubit 2 from 0 to 1, conditioned on the fact that qubit 2 is in the excited state. So this would correspond to this, I guess, and this would correspond to this, I think. Yeah. My drawing is maybe not to scale, but this is correct, I think. Okay, so how is this helpful for us? Okay. This is basically all we need in order to be able to create pulses on our system. Okay? If you want to make single qubit pulses, we already saw that. This is trivial. You just apply RF pulses and you rotate the qubit. Now, if you just apply pulses, what's going to happen? Anyone? Does anyone know how to create 2 qubit gates out of this? What happens to single qubit gates in this picture? Okay, so let me write this down. So what the system gives us, it gives us now 2 possibilities. Write this in big. We can do what are called unselective pulses, okay, or selective pulses. So when you have a spectrum, if you're applying a pulse, what do you do when you apply a pulse? You have a certain carrier frequency and you turn on your pulse, and after a while you'll turn it off. Now for simplicity, and this is actually how it's usually done, let's assume that we're doing a Gaussian pulse. Why a Gaussian pulse? Because if I do this in the time domain, I Fourier transform it, it also looks like a Gaussian in the Fourier in the frequency domain. Okay, so I can draw Gaussians everywhere in time and frequency and never get confused about it. Okay, if I now apply a pulse, a very fast pulse, onto the system, it will look something like this. If a pulse is fast, it will catch a large spectral width in the frequency domain. Okay, it means it's catching many frequencies. So if I do a very fast pulse, this transition and this transition are effectively going to see the same thing. Okay, those are unselective pulses. They're very fast. Okay, so this state and this state are going to evolve the same. So I can do a pi pulse or a pi half pulse, and they will rotate at the same angle. On the other hand, if I now apply, maybe I'll use a different color. If I now apply a very, very slow pulse, a slow pulse much slower than J. So selective pulses, we're going to do, let's have some time scale. Tau is going to be much smaller than 1 over j. If I apply a pulse which is much slower than 1 over j, so it ramps up, it's this really, really long, slow Gaussian, what's going to happen in the Fourier domain? What is it going to look like?
Very narrow.
Okay, exactly. It's going to be very narrow. So now I can select to give my pulse either at this frequency or this frequency. So suppose that I selected at this frequency. If it is very narrow, it will just create this transition, which is a conditional rotation now. Okay? This pulse will rotate qubit 1 conditioned on qubit 2 being in the excited state. And this rotation, and this pulse will rotate qubit 1 conditioned on qubit 2 being in the 0 state. Okay? So by doing these very slow selective pulses, we can do conditional gates. This is our 2 qubit gates. And by doing fast unselective pulses, well, fast pulses, they're unselective, we're doing unconditional gates. Okay, of course our fast pulse needs to be fast, but it can't be too fast because you don't want it to catch the other qubit. Really what I should do is add like 2 little lines here. These two are very far away from each other. They need to be far away enough from each other so we can do unselective pulses on this qubit without hitting this qubit, which is not exactly like I drew it up here, but you understand the picture. Okay. Now, in practice, what is done in NMR is not that a very slow pulse is created. A lot of the time what they do in NMR is they do an unselective pulse, a very fast pulse that does a pi over 2. And then in that frame what happens is that this transition will rotate in the opposite direction to this transition over here. Okay, so you do a pi half pulse, and then each transition is rotating in its frame in a different direction. And then after a time of j, you simply apply another pi half pulse, and then one of the state gets mapped down to 0 and the other one gets mapped down to excited. This is exactly identical to doing the selective pulses that I showed you. Okay? Technically it achieves the same result. So you can either do 2 fast unselective pulses and do a waiting time in the middle, or you can just do a very long selective pulse. It is the same thing. Okay? Are there any questions about how we do these single qubit gates and 2 qubit gates in an NMR? Okay, so congratulations, you know how to do gates on an NMR system. Now we only have 2 more things. Sorry, one more thing, the initialization. Okay, so we have a system, we know how to do gates on it, but now we need to be able to initialize it. And if you remember, an NMR system sits in a liquid. Liquids you get at room temperature. Which means they're hot. Okay, these liquids are hot. And it means that the spins are going to be in what? What happens when you have energy levels and there is finite temperature? What do we get?
Excited states.
Yeah. Are they distributed in a certain way?
Gibbs distribution.
Boltzmann distribution.
Yeah,
right?
exactly. Boltzmann distribution. Okay? So exactly like you said, the spins are in thermal equilibrium. Okay? We have 10 to the 23 spins, but on average, only a little bit of it is in the direction of the magnetic field. So the magnetization is tiny. It is a very tiny fraction. We get this thermal distribution. Now, if we take, for example, 500 megahertz, right? This is, we said, the splitting for the 11.7 Tesla of the hydrogen, right? Am I correct? That was the hydrogen. I think so. Let me check that I'm not wrong numbers. Yeah, that was the hydrogen. So if we take this, this corresponds to what temperature? H-Ni KBT. 500 megahertz corresponds to about 25 millikelvin, if you do the math. That's a very, very low temperature. And the Boltzmann distribution is exponential, right? It is e to the minus EI over KT. So if we're at a temperature of 300 Kelvin, even if we're at a temperature of, 20 Kelvin or 50 Kelvin, that's still pretty high. You need to go much, much lower than this temperature to get a substantial polarization. So at room temperature, when our solution is a liquid, our signal is going to be tiny. Okay? Now to solve this, you can also say, okay, let's just cool the thing down. Maybe there's, some liquid that can survive at 1 millikelvin. Also, maybe, cool it down, it'll be a solid, so what? Just use it as a solid, doesn't have to be a liquid. So just try to cool down to 1 millikelvin. The problem with that is it's really hard. Ten Kelvin, that's easy. 1 millikelvin is really hard. So the solution that they found for this, and this is described pretty nicely in the David Corey paper that I quoted for you last time, so please open it up, is something that is called a pseudo pure state. So instead of starting our ensemble of molecules in a truly pure state, we're going to initialize it in something called a pseudo-pure state. So if this is our room temperature distribution, so for our 2 qubits we have, this is 0, 0, for example. This is going to be exaggerated for clarity, but this is 0, 1, let's say. This is 1, 0, and this is 1, 1. And the y-axis, this is just the population. Okay, so the probability to be in each state, so this will all sum up to 1. Now if you were to take the system and really cool it down, so real cooling, would ideally bring us to the following situation, that everything is in the 0 state and we have almost negligible population in the other states. What we're going to do is I'm going to show you a procedure that does effective cooling. From this state, the sequence of pulses are going to create this state, the following distribution. So still, most of the population is going to be in 0, 0, but we still can't get rid of higher level distributions, but they're going to be all equal. So basically we're changing the distribution from a Boltzmann distribution to something where everything is in the ground state, but the population in other states are equal. And what I'm going to do now is I'm going to show you that, before showing you how to create such a state, I'm going to show you that given such a state, we're going to show that it basically transforms just like this state. And when we measure some observable, the average of some observable from an evolution on this state that started in this state, it will have the same information. We can extract the same information as the evolution starting from this state. And that is really all we're asking from the system. Okay? We want to initialize our system, do some algorithm, and then measure some observable, and we want to get this information. If we can do the same from some effectively cooled state, then we're achieving the same goal. Okay? So we're going to show you that such a state can get us to that goal, and then I will show you the procedure to generate that state. Okay? Are there any questions? No. Okay. So let's continue. Okay, so what we're going to do now is we're going to show that the following state, and this is, I'm writing now the density matrix for this pseudo-pure state. So the pseudo-pure state is just 1 over n. N is a normalization factor. I'll write it down in a moment. 1 minus alpha. Okay. Alpha is some number between 1 and minus 1. Times I. I is the identity matrix. Plus 2 alpha, 0, 0, 0, 0. Okay. This is basically our psi 0, 0, or psi 0, call it. Okay. This is our initial state that we want to be in. And this is our pseudo-random, pseudo-pure state. And, I mean, you can do the math in your head, but I'll just write it down. It's simple. 1 minus alpha, 2 to the power of n, plus 2 alpha. Okay. Where n would be the number of qubits. And alpha is between 1 and minus 1. Now if you take this pseudo-pure state and you transform it, so now we do transform it under some unitary u. So rho of t is going to be u of t rho naught u of t dagger. Okay. So we're propagating it in time. And you can see that this is just going to equal 1 minus alpha. Okay, you can plug this thing into here. It will be 1 minus alpha plus 2 alpha u psi naught u dagger. Yeah. I guess 1 over n. Or 1 over n tilde might be a little different at the end. Okay. So transforming this state is basically like transforming that state. You have u operating on psi naught plus this additional part which is proportional to the identity matrix. Now, if we take the average of some observable, okay, so take some operator A, and we take the average, so we're doing trace A rho. This is what we want to measure. We have some operator A, and the average of operator A is trace A rho. So we can calculate that. And this, again, up to normalization factor. Oh, maybe I'll do this. Then it's up to normalization factor. 1 minus alpha trace of A plus 2 alpha trace of A psi psi. Okay, there we go. So this is going to be the result of what we get in our detector when we look at the average. Now, this thing we can calculate. We know A. A is what we decided that we're going to measure. So we know this, so this we can calculate. And this we can figure out, and this is the result that we want.
Did you define psi as u psi naught?
Yeah. Yes.
Okay.
Yeah. Do you want me to write it explicitly? Psi? Like that? Yeah. Well, this will be, sorry. Like that. Right? Because this is a matrix. Like that. Okay, so now the question is, how do we create such a state? How do we create such a funny state, and what's the cost of creating such a state? And the way to do this is by using permutations. Okay? And after this we'll take a break, okay? But I just want to finish this. Okay, so how to prepare a pseudo pure state? Well, the idea is to permute. Okay, we start off, our distribution starts off something like this. So this is for a 2-qubit system. Okay. And now we can apply pulses. So suppose that we apply the following 2 pulses. We're going to apply a pulse that takes this population to here, and then another pulse that takes this population to here. Okay, and then we will get the following distribution. This is going to be level like that. Okay. Small. See, something like this. So what I did here is we apply 2 pulses, one that permute these 2 and one that permute these 2. And we get this distribution. Now we're going to start off again with this thing. And we're going to apply 2 different pulses that permute these 2 and permute these 2. Was that a question? No? Okay. Like, something like this. So what I did to get this permutation is to do a pulse that permutes these 2 and a pulse that permutes these 2. So from this distribution I can get this distribution, and from this distribution I can get this distribution. But now, note what happens if I add these distributions up. Can anyone see what happens?
All of the other become the same probability?
Exactly. Okay. So suppose that you can take your whole ensemble, and now part of it you apply these pulses to create this. Then another part of it you create pulses to create this thing. If you take the average of everything, you're effectively starting with a pseudo-pure state. Okay? Now you can do this in two ways. Okay, so there are two options to do this. Okay? There are two options to do this. One is we can treat the whole ensemble the same and then run the algorithm once with this, then start again, do these permutation, run the algorithm with these permutation, reset again, do these permutation, run the algorithm for these permutation, and so on. Okay, so we'll call this many runs. Okay, and use pulses for each run. Okay, many runs, use pulses for each run. Okay, we need different pulses. The second method of doing it, can anyone think of a different method of doing it? Also, you want to create permutations, but here we're doing different permutations from run to run. What else can we do? Anyone?
Apply the same permutation.
What was that? Never mind. Okay. The other thing you can do is create a spatially non-homogeneous magnetic field. Okay? Such that you're targeting different areas differently. Okay? Think of it as you're applying this set of pulses on this part of the ensemble, and this set of pulses on this part of the ensemble, and this set of pulses on this part of the ensemble. So, if you're clever, you can use an inhomogeneous field to target different parts of the ensemble.
But then you have to mix it enough so it will be even all over the
yes.
The liquid, right?
Yeah, you're bringing me to one of the biggest problems with this, right? And I kind of wrote it down here. Basically, you need 2 to the n. N is the number of qubits that you have, minus 1 permutations. Okay. So you're losing a lot, and you're losing in SNR here. Okay. And in practice, while using this pseudo-random state technique at room temperature, you lose, and you know, and for algorithms and molecules of just a few qubits, okay, effectively you're losing on the order of 1 million in your signal to noise. Okay, so that's a big hit to take if you're trying to do something useful with this. Okay. And I guess this brings us to the final point of this NMR quantum computer, and it's the fact that it's really not scalable. It is not scalable because okay, so NMR is really not scalable. You could think of, creating some types of molecules, that are slightly bigger and slightly bigger. But at the end, you need to find, the first thing you need, right, is an appropriate molecule. And that's going to be hard to find. And the more qubits you have in that molecule, the more spectral crowding you'll get. Okay. Also, you have coherence times. Okay. The coherence times are a bit problematic because, and I think I skipped this, the J couplings that you get are on the order of tens to hundreds of hertz. Okay. Where the splittings of the qubits are tens to hundreds of megahertz. Okay, so the qubits are well separated in space, but the J couplings are tiny. Now the coherence times are, let's say, on the order of a second, but if our J couplings are on the order of tens of hertz, that means we can't do many pulses, many 2-qubit gates within a single coherence time. Okay? It means that we will need to either resort to some error correction that will effectively increase the coherence times, or find some way of doing larger interactions. Okay? Because our conditional gates, the 2-qubit gates, are very slow. Okay? So the coherence times with respect to how fast you're doing your 2-qubit gates are not that long. Okay? Now also we saw that the initialization is problematic. Okay. We're taking a big hit in the signal to noise ratio because of this pseudo pure state technique. And the other thing is the readout. Okay. The readout, if you remember, our signal that we read out is basically proportional to the magnetization. I think I wrote it last time down. So I'll write it again, not to get it wrong. It's basically, let me write it even better. Okay, like this. Our signal is some amplitude, let's call it V. Sorry, mu x plus I mu y, okay, which is just the trace of rho sum over k sigma x k plus I sigma y k. So the readout for the NMR, is there someone? Yeah, there you go. Toda Aviad. Okay. So the readout itself is also annoying in the sense that you're reading out the average of the variables. So if you have a certain algorithm, and we didn't go into the details of this, but if you have a certain algorithm, you need to adapt it such that the information that you're getting is inside the average of the magnetization. There are methods to do that, but it creates an additional overhead, okay? And it limits the algorithms that you can actually run on an NMR quantum computer. Okay? So this is kind of like the bottom line. And most of the work done on NMR, so this whole NMR started flourishing around 97, 98, with that David Corey paper and so on. And for about a period of around 3 years, maybe even more, There were many little demonstrations with NMR. Okay, Grover's search algorithm on 2 qubits, teleportation, Deutsch algorithm, and even factoring of the number 15, doing Shor's algorithm. Okay, so first of all, I recommend that you just go and search for papers within this time span of 98 till around the beginning of, somewhere around 03, 04, I don't know. There were many papers doing these algorithms on NMR, and I think at this point you have the tools to read those papers and go into the details and understand what they did there, how they did their processing, and go into all the details we couldn't go into in class. Okay? But really in those years there was a big understanding of where the limitation comes from, and that really this can't go further than maybe 10, 20 qubits. You can imagine going to a few tens maybe if you work really, really hard. Okay, but that still doesn't allow you for scaling or error correction or any of those things. And really the paper from David Corey from 97 has all this summarized very, very nicely there. Okay, so if you want to always refer back to something, that is the paper to look at. Okay, so are there any questions before we take a 10-minute break?
About the permutations,
yes.
You said we have to do an exponential number of permutations. So if we are doing so many permutations, we can just simulate everything on a classical computer. If we are doing an exponential number.
No, that's not true. You need to do an exponential number of permutations, but it doesn't mean that you can't gain some advantage. It's still not killing your advantage. It's not making your computation exponentially larger. But you do need an exponential number of computations. So if you have 100 qubits, now 2 to the n minus 1 is a lot of pulses to give. Okay, it gives an overhead. Okay, and you take a hit on the SNR, because effectively think of this is all my 10 to the 23 small quantum computers, but really you're cutting down by that number because of those permutations. So you're like, think of it, you just have these little sub-ensembles, and each sub-ensemble is giving you one part of this permutation. This is where the hit in the SNR is coming from, but it's just hit in the SNR. Okay.
But you also have to compute the permutation, so you do have to compute exponential number of computation, right? How do you know which permutation to do?
Well, that's easy to do. Calculating which permutations you need to do, that's an easy function to do. You can write it on your computer. If I give you 100 qubits, you can calculate the 100 permutations very easily. It's not a hard computational task.
It's 2 to the 100, no?
It's 2 to the 100 numbers, but it's not hard to figure out what those 2 to the 100 numbers are.
But if you do, a classical computer cannot compute 2 to the 100 numbers.
Well, your computer, you can punch in the number 2 to the 100 in your computer. It knows, it can do arithmetics with such large numbers.
Yes, of course, but you have 2 to the 100 different computations, right?
No, I have 2 to the 100 different permutations, okay? 2 to the 100 different permutations of pulses that I need to give. And this is what we'll think about. You take your whole ensemble and you're dissecting it into 2 to the 100 parts. And this is your hit in your SNR only. But it's not hard to calculate how to cut up this ensemble. Well, in practice it would be hard to do like a gradient field, cutting it up into these 100 pieces. That might be hard. Physically it will be challenging to do. But just to calculate these permutations, that's not a hard computational task.
Okay.
Okay. Any other questions? Okay, so let's take a 10-minute break.